MacMaths, let's do some maths today. Okay, guys, we're still in lockdown, so we're going to start the A2 course now. So we're using the new books that you've all just picked up, the Edexcel Year 2 books. It's not all bad news, of course. Let's just move. Oh, forgot to move that out of the way when I was singing. And it's not all bad news because if you remember, I found these in the stationery cupboard at work, so swipe them straight away. Chuffed to bits, absolutely chuffed to bits to be using those today. I'll just put those there, take them out. So I've got some nice new colours. So we're going to do not all of the sections because some of the algebraic methods section, but the first one, the first exercise, is a very small exercise on proof by contradiction, the dreaded proof by contradiction. Basically, you've got to do all of those questions in that one exercise. It's not very long, it won't take you very long, but you'll get stuck on them all. They actually explain how to do each one in the back in the answers line by line, so there's no point in me really spending a lot of time going through the questions with you. So I'm just going to go through a few points. It's one of those things that you just got to practice by doing a few of them. And it tends to be the ones that I tend to look up solutions for if I'm looking up solutions for everything. There's no set method. It is just thinking really and trying different things. Anyway, so I'll go through a few things with you to help you with this exercise. So I want you to just going back to basics. I want you to think about how we describe integers, so whole numbers. I don't even know how to spell it. Is that an A or an E? I don't know. How we describe them, we can describe them by using the letter n, can't we? So n represents any integer. So from that, just remember that even numbers, mathematicians represent even numbers by doubling this. So if this is 1, then we double it and it becomes 2, or if it's any number sort of doubled is always an even number, isn't it? So 2n is a way of representing any even number. An odd number, if we wanted to represent algebraically an odd number, of course, the way that we can represent an odd number is it's always one more or one less than an even number. So we can write it as 2n plus 1, but we could easily just write it as 2n minus 1 as well. This is, that would always represent any odd number, no matter what the value of n is. If n was 5, 2 5s are 10, plus 1 is 11, it's an odd number. If n was 6, 2 6s are 12, add 1, it's 13, it's an odd number. Okay, consecutive numbers. You'll remember this, you will have come across these, so that's one after the other. So if mathematicians are describing consecutive numbers, they usually use n and then n plus 1 and n plus 2, for 3 consecutive numbers, or you could again easily use n plus 1 and n minus 1 as 3 consecutive numbers, so be aware of that. Now once you've got those, it's well worth just thinking about just simple things like, what do we get if we add 2 odd numbers together, 2 even numbers, an odd and an even, and multiply 2 even numbers and multiply 2 odd numbers and multiply an odd and an even. It's worth thinking about those things just to get you into the frame of mind of the things that you're going to use when we're doing proof by contradiction. So for that, a couple of things really. Just highlighting something. So odd numbers, because even numbers are numbers that you can always take out a factor of 2. So for instance, let's just explore this a little bit, for a moment. If you had an expression, let's just make something up, I don't know, a quadratic expression, 4x squared plus 10x plus 13. We've got a quadratic expression, and obviously if we put an integer in there for x, is this going to give us always an odd number, an even number, or an odd or an even number? Well, you can look at it and actually it forms this here, because actually we can write it as 4x squared plus I mean, just to go over the top a little bit, we can write it like that. So we can split up 13 to 12 plus 1, and this bit here now, you can see, can be factorised, can't we? We can take out 2. So we could have 2x squared plus 5x plus 6 plus 1. And so it doesn't matter what your value of x is that you put into there, into this original expression, because if you double it, you're always going to have an even number, and then if you add 1, it's always going to be an odd number. So this expression itself, you know, is always going to be an odd, and the proof of it is this here. You know, it lines up nicely, doesn't it, with this 2n plus 1 is a definition for an odd number. So, you know, this has to be even when it's been doubled by this 2 here, plus 1, so it's always going to give us an odd number. So, you know, just getting you into, you know, the practice I was just talking about. I know I'm rambling a little bit, but, you know, if you think about, you know, an even plus an even, you know, so it's worth thinking about that. An even plus an even, so that must be a 2n plus a, you know, a 2n is going to be 4n, and that factorises, you can take 2 out of that, so it has to be even, so it's always going to be even. That's proof that it's going to be even. And if you did an even plus an odd, it's like going 2n plus 2n plus 1. You've got 4n plus 1. That bit factorises, so that's even plus 1 is, so it's going to be an even plus odd is always going to give you an odd number, because it, you know, it matches up with this, doesn't it? And an odd plus an odd plus an odd, you know, it's going to be 2n plus 1 plus another 2n plus 1. It's always going to give you, you know, 4n plus 2, and that's always going to factorise, isn't it? So it's always going to give you an odd plus an odd number is always going to give you an even number for any value, you know, then. So, okay, so it's worth thinking about that. And of course you can do it with times as well, and even times an even, you know, just do that one and leave it there, and you can do the others. And odd times an odd, it's nice because you get a little quadratic that you multiply out, but you'll see that it's odd when you do that. 2n squared plus 4n squared plus 4n plus 1 you end up with. But even times even, you've got 2n times 2n, which is 4n squared. And, you know, that can be factorised, can't it, to 2n squared like that. So it doesn't matter what that gives you. Okay, but you know, by times and by 2 anyway, that's going to be even. Times 2 is going to be an even number, isn't it? Okay, so it's worth, you know, just playing around with those, because you're going to need those. Another little bit that I'm going to move on to in this lesson as well is this sort of rational numbers. Okay, so rational numbers, what are rational numbers? So rational numbers are numbers that actually we can identify somewhere on the number line. So they're all the integers, but they're also the numbers in between that have fractional, you know, values. Okay, and if they've got fractional values, they can be written simply as one number over another number, whether that is between 0 and 1 or bigger than 1, and as a top-heavy fraction. So, you know, a third is a rational number because, you know, between sort of 0 and 1, we can identify a third on the number line. It's exactly in that position, isn't it, if we divide that line up into 3 equal parts. So a third is a rational number, 1 is a rational number, 2 is a rational number, and so on. But there are certain numbers that are irrational numbers, and I'd write that down, irrational, but I don't know how to spell it. I don't know how to put whether it's 2 R's or 1, so I'm going to leave that. So an irrational number is a number that can't be put on a number line. And, you know, ancient mathematicians realised this. It happens with pi, doesn't it? Pi is that we know whereabouts it is. You know, we know it's, you know, further along here. When we get to 3 and a bit, you know, there's 3 on our number line, there's 4, and 3 and a bit, sort of around 3.141, you know, is pi. We can't actually place it, we know it's in a region. So it's what we describe as an irrational number because we can't physically put it in an exact place on the number line. So it's an irrational number. It's the same with square roots, okay? So, you know, you get that square root. The square root of a non-square number gives you that. If you press your SD button, it gives you that long screen, isn't it, full of decimal places that go on to infinity. So, you know, square roots of non-square numbers are also irrational numbers. And it leads me on to a very, very common proof that I'm going to go through with you now. And it is a way of giving a good example for proof by contradiction. Okay, and it shows the use of proof by contradiction. Okay, so here it is. And it was a very famous mathematician from antiquity called Euclid. Don't know how to spell his name. I think it was that. And Euclid did lots of proofs, but one of his proofs was that root 2 is irrational. I'm going to go with two R's. And so this is a very famous proof by with mathematicians that root 2 is irrational. And he does it by proof by contradiction. It's the classic, the quintessential proof by contradiction. And here it is. Because we can't describe an irrational number by anything, but we can describe rational numbers by a fraction. What proof by contradiction does is what you do is you provide what we call a negation statement. A negation is the opposite of what it is. So we assume that root 2 is rational, first of all. And what we do is we assume that root 2 is rational. That's the negation statement, the opposite statement, the contradiction, if you like. And then we prove that it doesn't actually work if we do that. If we make that assumption, it doesn't actually work. Okay, the statement that we made, and that is proof by contradiction. So you sort of end up with going, no, hang on, that doesn't work. So here it is. So if we say that root 2 is rational, we're saying that root 2 can be written by one integer over another integer. Now let's just have a think about this before we start. That fractions have a property, don't they? You can cancel them down into their simplest term. So imagine that a over b can be cancelled down into its simplest term. At some point with any fraction, you reach its simplest term. So you can't keep cancelling down, you know, forever and ever and ever. Once you get to sort of two prime numbers, if you like, or a prime number, you can't cancel it down anymore, because the only factors, you know, the only common factors are going to be 1. So all fractions can only be cancelled down to a certain point until we get to their simplest form. You know that, of course. Okay, so here we go. So if we're saying that root 2 is rational, it can be written by a fraction, because a fraction we can put on a number line. So therefore, if we make this statement must be true if it's rational. So if this statement is true, if we square both sides, we get 2 is equal to this squared is a squared over b squared, isn't it? And if we move the b squared over, we times both sides by b squared, we then get 2b squared is equal to a squared. All right, so that's what we've formed by saying this is rational. Now if we're saying that, then we're saying that a squared is an even number, aren't we? Because it's whatever b is, or whatever b squared is, it's double that. So it's an even, you know, this must be an even number. Okay, so a squared we could write as it's an even number, so it's 2n. Okay, we could write it as 2n. Oh, so because because it's a square. Oh God, hang on a minute. Because an even times an even is even, okay, that means that a must be even itself. Okay, from, you know, the little work that you will have done. So for this one, then we're saying that if we say that a squared is even, then a must be even, and we can say we can write a as 2n, so 2n squared. There we go. Okay, we're on the right path now. 2n squared, of course, is 4n squared, isn't it? Okay, 2n times 2n. And if we divide both sides by 2, okay, we get b squared is equal to 2n squared. Okay, divide both sides by 2. So now from that we can see that we're saying that b squared must be an even number, and so that b must be an even number as well, because it's 2 times sort of n squared, this here. So b must be even. So now we've just shown that a and b must be even numbers. Okay, so if we use different letters, we can say, I don't know, 2n for that, but we'll use k for that, so 2k for that. Okay, so we're not using, you know, the same letter here. So by saying that root 2 is equal to a over b and following this path, we can actually show that they must both be even numbers. If they are both even numbers, of course, then we can cancel it down, can't we? So we can divide by 2, which is not what we're saying here, but anyway, it doesn't really matter. So we're saying now that root 2 can be written by n over k. And by saying that now, because we've cancelled it, it gives us originally it gave us 2 factors that we can cancel down by dividing by 2. We're now back to this stage here, and if we go through the whole process again, instead of a and b with n and k, we can get to the point where we say that n and k can be written as 2 other, you know, even numbers that can be cancelled down. And we could keep going in this continuous loop, a ridiculous loop of saying that we can carry on cancelling down. So, and we can't keep doing that, you know, because a fraction has to reach a point where you can't cancel it down. It's in its simplest form. And what this is saying, because we go into that loop and do it again and again and again and again, it's saying that root 2 is creating a fraction that is infinitely, we can just infinitely keep cancelling it down, which is absurd. And so, because this doesn't work, we're saying now that root 2 cannot be rational. You know, it's irrational. Okay. And that is, you know, it's a very sort of famous proof for root 2. It's what Euclid used to show that root 2 was irrational, and it's a proof by contradiction. Okay, I hope my rambling made sense. It is good to play around. It's a proper sort of thinking side of maths, and it is good to play around with, you know, I talked about that even number squared. You try and square an odd number, for instance. If you square that, you would always get an odd number. So the fact that this was squared, you know, because this here would be like that 4n squared plus 4n plus 1, it would always be odd. So if a squared is even, then a itself has to be even. So so it's good, you know, in that, like so, you know, at the start, if you just have a sort of go with that. Okay, so these are the skills that you need to sort of practice with. Okay, the tools that you're going to use. You know, your n, your 2n, your 2n plus 1 for any number, even numbers, odd numbers, consecutive numbers obviously, and rational numbers. And that's enough tools now to have a go at the exercise. I'm going to do just a tiny little bit of lesson support, so I'll do a lesson 1A, which I'm going to do now, and just go through literally a couple of questions and talk about that exercise in the book. Okay, thanks for listening. Oh, sorry, I only used red and blue, but I'll try and in some of my other videos use green and black as well. Okay, don't spend too long on this exercise. It's just one small exercise, and it's, you know, it's hard to explain really. It's just fiddling around, and it's best just to come back to this before the exam. You know, the other lessons that we do, you know, proper sort of lessons, and there's proper methods, and they're all the same, and it's dead easy, and maths is dead easy, it's all logical. Okay, this is a little bit airy-fairy. Okay, bye-bye.